We have a great pleasure to have Pisin Chen from National Taiwan University. He will talk about information loss problem and analogy of black hole view laser experiment. Please go ahead.
Thank you very much for the invitation, and I feel very honored to give this talk. And so without further ado, let me begin. Let me see, just a second. How do I turn page? Yes. Can you see the screen well? Maybe.
Yes, very good. Very good screen.
Yeah. So let me wait for a few seconds. I can see the auditorium at YITP, where my second page is still not shown. Can you guys see?
Yeah.
Oh yeah. Now it turns. So can you see the new page?
Yeah, we can see.
All right, great. So first a brief, but also strongly biased brief history of the information loss paradox. This was first pointed out by Hawking himself soon after his seminal discovery of the black hole evaporation, as we all know. But near 50 years since then, there's endless debate. And the solutions is no lack of supply from the black hole complementarity and the counter-argument about firewall, then the entanglement between Hawking radiation and partner particles by many authors. And I particularly like to mention Frank Wilczek's 1987 paper. I feel it was quite penetrating, and that was actually the genesis of my later idea of this proposed experiment. So there, and so then there's the discussions about whether Planck-sized black hole remnants plays any role in this paradox. And there was also the argument against the firewall conjectures. Then more, I think many of us remember Hawking, Perry, and Strominger has a series of works about invoking the BMS symmetry to argue for the software hairs. But that also, by the way, and I'm lack of space to write, but you also recall that Raphael Boussole and Steve Giddings also made arguments that these software hairs do not carry information. Then there's of course a long history of Unruh and Wald's argument that there's nothing wrong with information loss, but I think by now most of us tend to believe that information is indeed preserved, and the issue in more recent times is becoming how this was preserved rather than whether it is preserved. And in the past several years, there's been the exciting islands conjecture and replica wormholes, etc., based on string theory or motivated by. Then there's a more recent effort by Misao Sasaki, Donghan Yuan, and Jungi Yun, and myself in the last year or so, more than a year, to based on the Euclidean path integral approach and with the multi-history scenario, which I will come to be the focus of the first half of my talk. So taking from the entanglement entropy point of view, let's review the issue of black hole information paradox. First, let me quickly reveal the classical picture. So we all know the so-called black hole thermodynamics. So the black hole is considered as a thermal body with a temperature, which is 1/8 pi m. Now, for simplicity, and like everybody else, we focus on Schwarzschild non-rotating stationary black holes. And so these were, of course, great contributions. And there's the Bekenstein-Hawking entropy that goes like the black hole area divided by 4, that we are also familiar. Now, this together, from the thermodynamic point of view, permits the emission of radiation, and therefore the black hole should gradually be evaporating away. Now, with this page and the following pages, 3 to 17, I took these slides are taken from Misao Sasaki's recent seminar at KEK in June, which was based on quite several of our recent joint publications. So I beg for your understanding that these are taken from his slides. So now let's turn to the quantum picture. Then the canonical interpretation then or derivation of Hawking radiation, it can be based on Bogoliubov transformation of vacuum. Now, the state inside the black hole, let's call it B, is then entangled with the state outside, A. The total wave function, let's say, is psi, then the matrix density is rho, and the reduced density is well known as shown here. The entanglement entropy, which is defined as the trace of the reduced matrix rho A times log of rho A, and this is let's call it S sub A is equal to F sub B. After evaporation, as the black hole disappears, the B part turns into void, and so SB is 0, SA is also 0. Now there is a contradiction because the the entropy of the black hole should have been the same as the Bekenstein-Hawking entropy, and that was also the radiation entropy. So there is an inconsistency, and actually this it's already can be clearly seen from the non-hyperbolicity in this conformal diagram. Now, now one well-known rescue comes from Don Page. Page asserted that entanglement entropy shouldn't exceed the Bekenstein-Hawking entropy. So since the black hole is continuing evaporating, so if the black hole Bekenstein-Hawking entropy started with BH0, and it just continued to go down, and let's imagine this is a log plot, then and correspondingly the Hawking radiation entropy just keep going up, and it's the difference between the two. Now, with this assertion, then about roughly half the time when the black hole mass is reduced to about half, the entanglement entropy then should start to go down, bounded by the Bekenstein-Hawking entropy. Now, so fine and well, and this is well known, the Page time, and this is the curve for the entanglement entropy. Now, this can preserve the information, and but there are questions. First, can quantum gravity effects be significant? We can ask ourselves, when the black hole is still macroscopic. Actually, most astrophysical black holes are macroscopic, and this half time even, down to half time, the black hole mass can still be huge. Now, second, is this Bekenstein-Hawking entropy really the absolute upper bound of entanglement entropy? Now, the recent islands conjecture computations seems to support these, but is that unchangeable? Now, so since we take the Euclidean path integral approach, so let me quickly review a little bit here. So let's take a conservative approach and consider semi-classical wave function. Then at semi-classical level, the wave function follow the Wheeler-DeWitt equation, and in the semi-classical history or under this picture, then are described by the WKB wave functions, as shown here, where S and the Euclideanized M action, S sub E, are both much larger than 1 and are on-shell. Now, Hawking radiation that may then be regarded as the quantum tunneling via instantons, and this was suggested by Sasaki, Yon, and myself, and also Dominique. Now, so here B is what's called the bounce action, and the it is so the probability, which is e to the minus b, goes like e to the minus 4 pi and m squared and minus m to minus omega squared. And this actually is the about roughly e to the minus omega over b over t as what Hawking radiation should be. Now, this there is an important implication, however, which is that this implies that there should be a tunneling, should be a possibility of a tunneling channel or instanton that goes from the black hole geometry to a no black hole geometry, a trivial one, Minkowskian. So in that case, it is your e to the minus 4 pi m squared. Now, by the way, it's just a kind of a footnote. The idea of tunneling between semi-classical histories was also investigated slightly earlier than us by Jim Hartle and Herta. All right, so to be more specific, we consider an action in the Euclidean geometry is Einstein plus a massless scalar field, as shown here. Then the classical solution is just simply R equals A pi grad phi squared. The on-shell in Euclidean action, in addition to the boundary term, and there's also the contribution from the horizon, and so it as shown here. Now, so the bounce action, please consult the paper by Gregory and Moss. So the bounce action then is the Euclidean action with instantons and minus the Euclidean action with the background. And this, by the way, can be intuitively appreciated through the thermodynamic picture. And the free energy is like the energy emitted and minus the original, the entropy of the body. Now, so now, as I argued, this Euclidean instanton picture allows the possibility of tunneling from a black hole geometry to a non-black hole geometry, as you now see that the singularity goes away and the Minkowski spacetime is recovered in the form of a radiation shell. All right, and so here is the thin shell and the background, the instanton tunneling and the background. So it is a whole circle minus half a circle, and you got 4 pi m squared here. So this is theoretically allowed. And so let us imagine the following picture of that deals with the black hole evaporation as a multi-history classical history tunneling. So imagine the following: you have an initial state here, and so this is the event horizon, and imagine, evaporation. Now, our the Euclidean path integral formulation allows us to consider multiple semi-classical history and so as the final state. So what we are considering, and in a sense, assuming that information is indeed at the end of the day conserved. So, and we also know that initially during the black hole evaporation, the information is losing. Now, this tunneling helps to save the day to tunnel into an information preserving history. So that's the global picture. Now, since this can happen in the world of Euclidean geometry, we imagine ourselves, turning the Lorentzian space-time into Euclidean, and at the end of the day, after the tunneling, and we ask what's happening to the universe, we translate it back to the Lorentzian space-time, and so imagine the initial state goes into some Fj final state through the path integral, and just a quick reminder again, this Euclidean action is on shell. So the tunneling mediated by the instantons are during this time, through here, and the tunneling probability once again it goes like e to the minus b, where b is the bounce action. Now in this case, when the black hole is eventually tunneling into trivial geometry, the bounce action is 4 pi m squared. Now, so let's take a look of the somewhat more microscopic picture. Then the universe then can be considered as the sum of the history, probability of two parts. This, let's say, is the state of the black hole, and this is the psi j describes what's outside. Now, now psi j itself is you can say classical. This is the whole picture. This is a wave function, but it is a summation of its underlying quantum states. Now, these are the requirement for the conservation, so unitary. So now, having this, you see that there is a decoherence that must happen between classical states, and the density goes like this thing, cat graph and so on, and then you take the trace, and the reduced density matrix then goes like that. All right, so here is the B, and this stands for A. Now, so now let's identify phi as the history, the black hole part, which is losing history, and the psi j is with no black hole at the end is an information preserving history, and the total entanglement entropy is then roughly equal to p squared s phi entanglement plus the sum over all the j states of qj squared times s entanglement of psi j. Now, in the part of the information preserving, at the end of the day, as I said, the B region, the B part disappears. It turns into a void, and this is our picture. Now, p squared is the so-called the persistent probability of the evaporating black hole. Then under this picture, the page curve is obtained if p squared initially is of the order 1 and it goes to 0 at the end at late times. Now, as the transition from black hole to with mass m to a trivial geometry, as we discussed just now, with a single instanton has a probability of e to the minus b, as we already said. Now, how about because it's path integrals, you have many possibilities. The n instanton transition then corresponds to a bounce action that goes like 2n minus 1 times s, the same as here. And the total will be the sum of n from 1 to infinity, and you get this 1 over e to the s minus e to the minus s. And then the persistent probability p squared can be solved, and you get this for the black hole geometry, and 1 minus p squared as the trivial geometry. So here's the plot for p squared and 1 minus p squared. And so you, as a function of s, then you see that how they go. And the probability to tunnel to a trivial geometry is clearly dominates at the end of at late time when the mass is much less than m0, and you can do approximations. Well, just by the curves you can tell. Now, what's the upshot? The upshot is that the page curve can be rederived, albeit being modified. So instead of this well-known triangle, now the maximum of the entanglement entropy is moved largely towards the end of the evaporation. So the page curve, if we call it, is seen to be largely skewed towards the late time. Now, then you may quickly ask, then towards late time, isn't the quantum gravity effects not non-negligible, and is this semi-classical picture still valid, this claim? And one can quickly check. As long as, well, the semi-classical approximation is valid for as long as the initial entropy S0 is much larger than 1. So take a physical example. If the initial mass of the black hole is 1 gram, then S0 is 10 to the 10. And the max, which goes like log of S0, is 23, still much larger than 1. So these pictures, you're one to say to trust this calculation towards the late time sufficiently. Now, there's another important implication of this modified page curve, which is that beyond the page time, it seems like that the entanglement entropy is not limited by the Blackenstein-Hawking bound entropy bound here, and so I have some comments in the next page. So then, so this, by the way, this seems to suggest that the existence of a black hole remnant at the Planck size, or so-called monster states, and so on. So a brief summary for the above. Actually, my talk is made of 2 parts, not unrelated. But the first part is theoretical and deals with some not quite mainstream, proposal or solutions, as I just reported to you, based on Euclidean path integral, with some rather semi-major modifications. Then, so please allow me to make a brief summary of this first part. Now, so what we propose is and I just said, Euclidean path integral approach under semi-classical approximation. And Hawking radiation can be viewed as a quantum tunneling under this picture. That implies that it is possible to tunnel, to have a finite probability to tunnel from a black hole to a trivial geometry. And this further implies the existence of multi-classical history. And in the end, at late times, trivial geometries probabilistically dominate the wave function. Now, the page curve is modified, as I just kind of warned you. Now, and then, another big claim is that it also violates the Bekenstein-Hawking bound. Recently, actually last year, there is another example of the investigation that found that black hole bound it may be violated. This was by Juan Infante, De Filippo, and Mokoyama. Now, let me turn to the second part of my talk. Yes?
Can I ask a question?
Yes, yes.
So, it is interesting, the violation of the Bekenstein-Hawking bound, but usually such a breaking of the bound comes from negative heat capacity of the system. So, in your calculation, I'm wondering, you used Euclidean path integration to compute the tunneling probability, right? But
yes.
in my guess, so in the calculation, can you see some appearance of negative heat capacity, or so?
Very good question. Very good question. I didn't think of it, but let me promise that after this talk, after today, I'll definitely look into it with my collaborators.
Okay, thank you.
Right. Thank you very much. So let me continue then. Can you see my new? Good. It's faster now, almost simultaneous. I mean, my change on your screen. So now, I think most of us in this audience and participation of the workshop sees that the investigations of this information loss paradox over the last nearly half a century were mostly theoretical, including my own recent investigations, for actually a pretty good reason, because essentially all astrophysical black holes, stellar size or supermassive black holes in galactic centers, etc., are in the Hawking sense are too cold and therefore too young. Take, for example, the lifetime of a solar mass black hole. The Hawking lifetime is 10 to the 67 years. Now, the age of our universe up to now is only 10 to the 10 years. So it is like an infant in the Hawking sense. But as you recall, most of the discussions, including my presentation just now, the end state, the late time, is the key on how to preserve the information, and yet our universe, the astrophysical black holes are just too cold and too young to address that. Now, I think Bill Unruh already saw that ages ago, decades ago. So he was seminally in 1981 proposed the idea of analog black holes, and his proposal with kind of a moving fluid, sound waves as what he called dump holes. There were no lack of additional suggestions since then, like Yablonovich traveling index of refraction. Then my own proposal with Toshiki Tajima on valence acceleration of electrons by lasers, and Unruh and Schutzhold proposed with the electromagnetic waveguides and even with experiments. Then in more recent years, Jeff Steinhauer in Israel has done a series of beautiful experiments based on Bose-Einstein condensate. Now, there's a long history of analog black hole, quote unquote, theoretically, in many of the standard textbooks, including the famous Brill and Davis book on quantum field theory in curved space, have invoked accelerating mirror as a good analog of the Hawking black hole. Now, this, of course, already was investigated soon after Hawking's by Fulling and Davis, Fulling, Unruh, and also Wilczek, 1989, Carlis Wiley, 87, and Hoda-san yourself with Schutz-Hole, Unruh, 2015, and I myself with Juramuru, 17, and with Yong Donghan, 27. So the idea, and this is also what Hoda-san you have shown. So imagine you have a flying mirror, and this is actually 1 + 1D. So I'll come into some other issues later. So imagine you have a mirror which was I think its whirl line just goes straight when it was not moving, and suddenly it decides to move, also move almost instantly, rather relativistically, and approaching the null rate that acts as the effective horizon, and then suddenly it decides to stop, and then it goes straight again, and during which the vacuum fluctuations, of course, there are many different possibilities. Some emerge and rebound, re-emerge, or some both hit the mirror and both reflected. But some cases you have one hit the mirror and the other will just follow along the horizon until the mirror decides to stop. And by then, there's no other ways. It has to be bounced. And then we call usually one that is emitted, the Hawking particle, and the vacuum pair that did not go along together. By the way, if they are both reflected, then the Heisenberg principle dictates that they won't go to the null infinity. They'll just recombine. So that doesn't count. And the only ones that count are like what we are drawing here. And the partner mode will have to be separated until the end. But in this picture, by the way, they're both moving in the same direction, the positive x direction. Now, whether at the end, whether it is a burst of energy like some suggest, or just evanescent into 0-point fluctuations, as Hoda, Schutz-Hole, and Unruh suggest, we don't know. So now the issue is there a chance that you can turn this theoretical study of a flying mirror as an analog black hole into reality? And this was what I and Juramuru proposed. And this turned out to be possible. Now, here is kind of a layman's kind of a cartoon to draw an intuitive correspondence. If you like, you can even imagine a local equivalence principle. So this is a black hole, and this is event horizon, and you have the vacuum fluctuations in the vicinity, and one gets climbs out of the gravity and goes to infinity with a strong redshift, gravitational redshift, whereas the infalling partners in our left plane still kind of almost forever slowly approaching the horizon. So there is like bubbles there. Now, in the case of flying mirror, then you are having a huge acceleration A, and then the vacuum, as I just described, just keeps it kind of coming out to the back. So the analog or analogy in this case is the Doppler redshift that mimics the gravitational redshift here. And the partner modes are indeed kind of sticked to the event horizon. Now, some of you may know, some may not. Juramuru, who is widely recognized as the father of the second laser revolution, received the Nobel Prize in 2018. And this, by the way, was a picture that we took in a reception hosted by the US Embassy in Sweden. Now, how much more time do I still have?
You have 10 minutes.
Okay,
10 minutes.
so let me speed up real fast. So this whole idea is based on what's called plasma wave field acceleration, first proposed by Tajima and Dawson, 79, to shoot a laser pulse into the initially quiescent plasma that would excite plasma waves. It's like a fluid. And then if you manage to inject a charged particle beam, such as electron beam, to ride on the right phase of this wave, then it can be like surfer being accelerated. Now in 85, Dawson and I, with other collaborators, suggested to replace the laser pulse with the high energy with an electron beam. Then it can equivalently excite a very strong wake, what's called the Langmuir wave. Now this can also do the same job. Now the laser-driven one has been, and both schemes are now becoming the leading major plasma wave field mechanisms pursued widely in the world. And a proposal in the recent past 10 years was by the proponents called the hybrid plasma acceleration, with an intent of taking advantage of the both schemes and combine into one. And so I thought that was the direction of the future. In the case when either the laser pulse or the charged particle beam is extremely intense, then the plasma wave is broken. It's becoming sawtooth-like, extremely strong. It's into the nonlinear regime, and that is pretty much like a tsunami. About 20 years ago, Sergei Bulanov and company suggested that such a very thin and intense wave field, which is just actually the plasma electrons that's coming back after the perturbation, can serve well as a piece of flying mirror. And in their idea, a laser pulse, a second laser pulse, hit right onto this plasma mirror, upon reflection, can enjoy an instant Doppler blue shift of 4 gamma squared, turning an optical light into X-ray for applications. So this was the original idea. Now, I took that idea over. We say, in fact, if your plasma has a changing density, let's say they're gradually becoming less dense, then you can imagine that the laser pulse can speed up because of the gradually change of the index of refraction. It's gradually becoming closer to 1, to unity. And we know, of course, in vacuum, it travels with the speed of light. And the light is slower when the density is medium is denser. Now, with that, then we can show that, and time is not sufficient, but let me just say, if you have a plasma density with some constant plus exponential behavior, then you can derive the mirror's acceleration. And in the limit where the target thickness is much larger than the characteristic gradient of the target density, then asymptotically you find this kind of trajectory, which is formalistically the same as the Davis-Folding trajectory. And that trajectory, if you transcribe into the advanced and retarded UV coordinates, you can see that for V smaller than A, it's reflected. For V larger than A, it will be undisturbed. And so V equals to A ray serves as the horizon. And then the corresponding Whiteman function can be derived with a response function like this. And of course, you got a temperature where it goes inversely proportional to this D. And a D, as I remind you, is the parameter that describes the gradient of the change of the target density. So that's the idea. And so 4 years ago, I pushed and organized a international AnaBHEL collaboration, which now consists of several institutions, including École Polytechnique in Paris, and also CEA Saclay, also in Paris, and then Kansai Photon Science Institute in Kyoto, and also National Taiwan University Center. So the strategy was to do some, actually majorly all the R&D of the key elements are carried out here at NTU, and it's with very good progress. The diagnostics of the plasma target density profile and its corresponding trajectory is to be carried out at KPSI. Indeed, we have already gone through our first, how should I say, data acquisition several weeks ago in early, during the summer. Then we are contemplating carrying out a full-scale experiment to detect the Hawking radiation and entanglement entropy at the new Apollon laser facility in Saclay. So this is a schematic picture of what we are imagining, and you have a laser pulse coming into the acceleration, experimental area, and you have a supersonic gas nozzle that shoots out across, and with a knife edge to create a shock, which, by the way, can give rise to a very sharp change of the density. And you recall that we like to have the Hawking temperature as high as possible, and so we like to have a characteristic parameter D as small as possible, meaning as large a change of density gradient as possible. And with a constant plus that, the density goes like this. And then the Hawking photons will shoot backwards with our detector here, and we are thinking of using infrared. And these, after Doppler redshift, are in the infrared regime. And I'll show you that we are currently doing R&Ds on superconducting nanowire single photon detector. On the other side, the partner modes, and I like to say that these plasma mirrors are not made of plasma electrons, and they are rather porous. Their reflectivity is not 100%. Actually, it's pretty low, like 1% or something. So essentially, all the partner particles, instead of reflecting back as in the diagram that I've shown you, at the end, when the plasma mirror arrives at the other edge of the plasma target, they will just simply shoot out, going forward without suffering the Doppler redshift. So these photons will be in the infra, extreme UV regime. So there are, of course, many test forces. I thought to this audience, I'm very eager to share with you that these semi-transparent plasma mirrors, and especially in reality, it's a 3+1 dimension. So it has a finite area and finite thickness. In the end, it's not so surprisingly, it has a emission probability that goes almost like black body radiation, but with a form factor. And so this is the key to share with you. And taking the assumption of 1 laser shot per minute and 8 hours running per day for 20 days, this is what information we got from Apollon laser as well as KPSI. Then one expect to have about 0.3 events per laser crossing. And in the end of this kind of a running, one will expect to have about 3,000 of such Hawking photons and their partners with this kind of a spectrum. And so let me say that the black one is the canonical black body spectrum. And with a finite size and plane mirror, just a finite size, you got this red one. And you see that there's a tendency of squeezing the frequency spectrum to a kind of sharper spike. And then when you also include the mirror thickness, then it's into this blue shape. And the corresponding angular distribution goes also like this, blue one here. And so this is to the benefit of the experiment. And okay, so let me continue. This is what called particle in cell simulation. People call PIC simulation. Very, very powerful tool in most of the plasma investigations of whatever. And this is our simulation that shows that a laser pulse induced plasma wake fields behind. Clear, it's very clear. And simulation also shows that the trajectory that with the assumed plasma density gradient, the calculated beta, this is the Lorentz beta, does agree well with the simulation. Now, the supersonic gas jet R&D has been going on well, and the measurements agree well with the simulation. And this is a raw data, having yet gone through the full data analysis, but I'm just eager to show you the couple of photos that we took from the recent KPSI run, and what our intent is to identify the wake fields and see and identify its position versus time to plot out its trajectory, and to see if indeed and under density gradient there is an acceleration. Finally, there's a brief report to you about the progress of the R&D on the superconducting nanowire single photon detector. By the way, the reason of looking for single photon detection is that, as I just shown you, the expected yield per single laser crossing is a fraction of 1, 0.3. And so most likely when you detect the Hawking photon, it is just 1 photon in the infrared regime. So it's you need to have the capability of detecting 1 photon, and nothing is better than a superconducting nanowire, which does the quantum jump to the normal conducting and give you the signal. And so here are the R&D using magnesium oxide as a substrate and the titanium nitride as the thin film, and this is what we shown. And then indeed the persistence from the superconducting state to the normal conducting state is extremely clear. And we have now developed the nanowire, and we are doing further improvements and doing the lithography and so on at NTU and at the nearby Academia Sinica, also in Taipei. And so let me stop here by saying that by summarizing, well, no, before the last summary, let me pose to myself a question. Now, the question is, how would this experiment address the information loss paradox? And my answer are the following. First, it cannot prove the loss of information because our lab is in the Minkowski space-time, and unitarity must be preserved, as we know well. And so there's no chance to do the otherwise. But as I said, by now, most people believe that information is indeed preserved. And the real question is, how is it preserved? So the utility of this experiment is to address the second version of the information paradox. Second, it can prove that Hawking particle and partner particle are indeed entangled. I forgot to put it down, but I like to say in my other talks that, in a sense, our proposal is a flying EPR experiment. Whereas the well-known EPR experiment initiated by Alan Aspect in the 1980s is in the lab ring, and you have the pair of photons, entangled. But here, our source, the flying mirror, is moving at near the speed of light, and so the correlation, the pair now has a huge dichotomy in their energies with the Doppler redshift, and this is rather interesting. And to prove that they are entangled, you also want to measure the opposite polarizations of these two particles, and which in our superconducting nanowire detector R&D is also under invest. Is one of our target to also measure its polarization. Now, Donghan and I have published a paper about the evolution of the mirror entropy, and including the scenario where the mirror is actually shattered, broken, and that may be a kind of a different rendition of the firewall conjecture. Finally, it would be interesting to find out whether the system is able to help investigate the islands or the replica wormhole conjectures. Actually, I've been contemplating about that. So here's the summary of our second half. And well, it goes with saying information loss paradox is one of fundamental problems in physics. So far, investigation is essentially theoretical, and observation of the black hole at the end stage unlikely from the astrophysical setting. Then quantum entanglement between Hawking radiation and particles may reveal the secret, and accelerating plasma mirrors may serve to address some aspects, not all, of this paradox experimentally. And finally, this AnaBHEL experiment is in good progress. Thank you very much.
Thank you very much. Very nice talk. Thank you very much. So, do you have a question or comment?
So can you estimate the page time of your experimental system if that exists?
It's not existing in the following reason. You recall that the page time, the reason of reaching a maximum and down was because in the first half there's the information loss history, because Hawking particles just keep leaving the black holes, and there's a information loss history. That part cannot be simulated in our laboratory.
Okay.
Our information is never lost. So in the sense, we are kind of cutting halfway in to simulate the late times of black hole evaporation.
I see. Yeah, thank you.
Sure.
Another question or comment? I have a question. So, I have much interest in particle detector, photon detector in your experiment.
Yes.
So, that is a single photon detector, right?
Right.
Single photon detector. Then, so can you directly measure the mode function of each particle, or just measure the helicity of the photons? So I'd like to know the spatial configuration of the mode function of the particle.
Okay. I'm not an expert in that part. My collaborator, Professor Stathis Paganis of NTU, who is a particle physics high energy experimentalist, and he is taking the lead in this part of the R&D. But I do know something about the physics of the detector, and I will consult with him. But my not very mature answer to you, I thought I would have an answer. You know very well about all these superconductivities. Now, what it does really, it's like a bit like squid. It is, this incoming single photon provides the energy or heat to gap up to bridge the energy gap, right? And so to kill that energy gap and therefore return to the normal conducting stage, my concern is that activity may not be sufficient to reveal its mode function. But the question is so good, like your first one. I like to also further look into that. Now, can you? Sorry, I shouldn't ask question, but I'd like to ask you a question. Can you kind of share with me what's the advantage of measuring the mode function?
Oh, I need some carbon calculation, so we can communicate with by email.
Okay, good, very nice. Yes, yes. We do. In my very naive thinking, I was thinking that there will be 3 attributes, maybe just 3 attributes of the correlation between the Hawking and the partner particles. One is their energy correlation, as I mentioned, this 4 gamma squared Doppler shifting, and second, their angular correlation, because their respective transversal momenta must be equal and opposite, and so the correlation between their outcoming angles are important. And the third aspect is their polarization, as I have already mentioned. Okay, if one goes this way, the other must the other way. So initially, when I posed these challenges to my colleague, Professor Pagani, he was a bit concerned because most of these single superconducting nanowire detector did not talk about polarization measurements, but with himself and his very outstanding students, this looks likely with a rather high quantum efficiency. So I'm glad about that.
Oh, great. Thank you very much.
Thank you.
So any other question, comment? So Pisin, so can you comment about the plasma wave field technology, which can be applied to another field like nuclear physics or the industry? So
yes.
Yeah. So
yes.
you should comment about that.
Sure. There are many potential applications. The original one, like what Toshi Tajima and I originally proposed, was to apply it to high energy physics, because we know very well that the colliders based on the copper tubes and so on has a rather low energy gain per unit length. We call energy acceleration gradient, and that's why the well-known LHC at CERN has 27 kilometers in circumference. Now, if you want to, and people are now considering 100 TeV colliders, then you have to have an even bigger collider size, right? And that typically the dominant cost of colliders is, first term is linear to the length of the collider. And so it's unthinkable. That's why about 40 years ago, we proposed to replace this with plasma acceleration, where the structure is already, how shall I say, broken. It's all in plasma forms. And the acceleration gradient can be at least 1,000 times larger. Instead of 100 MeV per meter, it can be 100 GeV per meter. And this, by the way, as I mentioned, shown but didn't go into detail earlier, has already been proven in the laboratories at SLAC, where people observed the gain of some tens of GeV within a meter. And so this is one major original motivation. But then it can also help to serve more kind of a practical issues, such as hospital use. The hospital needs linear accelerators, but currently it's too big, too expensive. And also protons are very good to do the cancer therapy. Currently using synchrotrons can also hopefully be replaced, by this. And also the very useful free electron laser, the source of that, GeVs of electron beams can be also provided by this. And so, and nuclear, thank you for just mentioning, nuclear transmutation and so in principle can also be applied by this idea.
Thank you very much.
Sure.
So the online audience, do you have a question or comment? No? Okay, so let's thank the speaker again. Thank you very much, Pisin.
Thank you. Thank you very much.